Hydraulic brakes are based on Pascal's law, Torsily's law, Newton's law, and Volt's law. So for what we have here is Pascal's law. Pascal's law states that the pressure which is applied at any point on an enclosed surface of a liquid, we have a liquid enclosed surface. So the pressure applied on any point of a liquid surface is it is distributed, it is transmitted equally in all the directions. That is what Pascal's law states. Torsily's law deals with the velocity of the liquid. Newton's law, that is the force, where it deals with the force. And then Boyle's law, it states with the temperature, which is inversely proportional to its volume. So for the hydraulic brakes, we have Pascal's law. So the hydraulic brakes are based on the principle of Pascal's law. That is, the distribution of the pressure which we are applying on the liquid is in all the directions. In a wind tunnel experiment, the pressure on the upper and the lower surfaces of the wings are 0.90 into 10 raised to 5 Pascal and 0.91 into 10 raised to 5 Pascal respectively. If the area of the wing is 40 meters square, the net lifting force on the wing is 2 into 10 raised to 4 Newton, 4 into 10 raised to 4 Newton, 6 into 10 raised to 4 Newtons, or 8 into 10 raised to 4 Newtons. So basically what we are given here is, now we will write the given data. Two pressures we have. The pressure 2, which is 0.91 into 10 raised to 5 Pascal, and pressure 1, which is 0.90 into 10 raised to 5 Pascal. That is the upper pressure and the lower pressure respectively. And then we have the area, which is 40 meters square. So in order, the pressure difference, there is some we have given the wind tunnel experiment where is the pressure on the upper and the lower surfaces. So the pressure difference which provides the lift in the wind tunnel, so the pressure difference that provides the lift, which is given by the pressure difference multiplied by the amount of area in which the pressure is applied, that is P2 minus P1 into the amount of area. So P2 we have 0.91 into 10 raised to 5 minus 0.90 into 10 raised to 5 Pascals into area is 40 meters square. So calculating this, we will get 0.01 into 10 raised to 5 Pascal into 40 meters square. So the final answer comes out to be 4 into 10 raised to 5 Newton. So we have B, 4 into 10 raised to 5 Newton. That is much of the pressure difference is required. Okay. A tank with a square base of area 2 meters is divided into two compartments by vertical partition in the middle. There is a small hinge door of face area 20 cm square. At the bottom of the partition, water is filled in one compartment and acid is filled in the other compartment respectively, of the density 1.5 in the other. Both to a height of 4 meters. The force necessary to keep the door closed is, so basically we have the options 10 Newton, 20 Newton, 40 Newton and 80 Newtons. So we will draw a diagram of the situation. What we have given here is, we have a tank which is divided into two compartments and there is a small hinge door closed out here, okay, and in one of the tank there is, and one of the compartment there is water, and in other compartment there is acid, okay. So the force necessary to keep the door closed, so we need to find the force which is required to keep this door closed. We have a 4 meter height tank, okay, they have given here the height, and the face area is 20 centimeters square, okay. So what we'll do is, first we'll find the pressure exerted by this water on the door, then the pressure exerted by this acid on the door, then we'll calculate the net pressure by subtracting both the pressures, and then we'll find the force. That will, we know the force formula, that is pressure into area. So we'll move on to that. Okay, now moving on to the next, moving on to that one. So for the water compartment, we have the height which is 4 meters. We have the density of water which is 10 raised to 3 kilogram per meter cube, and so the pressure exerted by the water on the door will be given by rho hg. We have given the gravitational constant, it is 10. So we have here is 10 into 4 into 10, that becomes 4 into 10 raised to 4 Newton meters square, okay, Newton per meter square. That much is the pressure applied by the water. Now similarly for acid compartment, For the acid compartment, we have the density given to be 1.5 into 10 raised to 3 kilogram per meter cube. Okay, the height is again 4 meters, and so we will be finding the pressure applied. So the pressure, which is again rho Hg, so rho will be 1.5 into 10 raised to 3 into 4 into again G, which is 4. So that comes out to be 6 into 10 raised to 4 Newton meter square. Okay, so this is the pressure applied by water, this is pressure applied by the acid. So we are calculating the net pressure applied on the wall, on the dough. Okay, so net pressure applied on the dough will be the pressure difference between the acid and the pressure difference between the water. That will be 6 into 10 raised to 4 minus 4 into 10 raised to 4. So that gives you 2 into 10 raised to 4 Newton meter square. Okay, now Newton per meter square. Now we are finding out the area of the door. We have given the area, that is 20 centimeters square. So we'll convert it into meters. So that gives you 20 into 10 raised to minus 4 meters square. Okay, now we'll calculate the force. We know it is pressure into area. Okay, so pressure, we have already calculated the net pressure, that is 2 into 10 raised to 4 multiplied by area, that is 20 into 10 raised to minus 4. That gives you 40 Newton of force is applied on the dough. Okay, so the answer is 40 newtons. Okay, the cylinder tube of a spray pump has a cross section of 6 centimeters, of which has 50 holes, each of diameter 1 mm. If the liquid flows inside the tube is 1.2 meter per minute, then the speed of ejection of the liquid through the hole is 2.1 meter per second, 0.31 meter per second, 0.96 meter per second, and d is 3.4 meters per second. So we have the given data here is the cross section of the tube, that is the area of cross section. We can take it as A1 of the tube, which is 6 centimeters square, which can be, we will convert it 6 into 10 raised to minus 4 meters square. Okay, then we have the number of holes. We have the number of holes, there are 50 holes. Okay, and each of the diameter of the holes is 1 mm. We'll convert it into meters, that gives you 10 raised to minus 3 meters. Okay, so the radius of the hole becomes diameter upon 2, that is half into 10 raised to minus 3. So that becomes 5 into 10 raised to minus 4 meters. Okay, that is the radius. So we'll find the area of cross section of the hole. So area of cross section of one hole, that will be pi r square. So pi into radius is 5 into 10 raised to minus 4 square. Okay, so that is the area of cross section meter square. So for the area of cross section of the 50 holes, the total 50 holes will become 50 into pi into 5 into 10 raised to minus 4 square meter square. Okay, so the answer is, we can get this as 50 into pi, A2 ka value, that is 5 into 10 raised to minus 4 square meter square. Okay, now we have given the speed. The liquid flow inside the tube is with the 1.2 meters per minute. So the speed of the velocity of the liquid, will take it as v1. So it is 1.2 meter per minute. So we'll convert it into seconds. So 1.2 upon 60. So that will give you 0.02 meter per second. Okay, so velocity of the liquid is 0.02 meters per second. Now we need to find the speed of ejection of the liquid through the holes. So V2 we need to calculate. We have the formula A1 V1 is equals to A2 V2. Okay, we need to find out V2. So the formula becomes V2 equals to A1 V1 upon A2. Okay, so we'll put on all the values. We have A1 out here, we have A2 out here, we have V1 out here. Okay, so A1 into A1 becomes 6 into 10 raised to minus 4 into V1 is 0.02 upon A2 is again 50 into pi into 5 into 10 raised to minus 4 square. Okay, after calculating the entire thing, the velocity V2 through the stream comes out to be 0.31 meter per second. So that is 0.31 meters second inverse. Okay, so option number B is the correct option. Okay, which of the following diagram does not represent a streamline flow? We have 4 diagrams here in which the streamline, the flow of the streams is given, the flow of the liquid is given, flow of the stream is given. Okay, so what we have is in a streamline flow, in a streamline flow the two streamlines cannot cross each other. Okay, they cannot intersect each other, so they cannot cross each other. So the option B, where they are crossing, does not represent a streamline flow. This is the correct option. An ideal flow of liquid must satisfy Pascal's law, Stokes' law, continuity equation, or Bernoulli's theorem. The correct answer is the continuity equation, because what we have in the continuity equation is that velocity is inversely proportional to the cross section area of the liquid, or of the material in which the liquid is, of the pipe in which the liquid is flowing. That is, the liquid velocity of any cross section is inversely proportional to the area of cross section of the pipe or that section. This explains why the speed of water emerging from a PVC pipe increases when we press its outlet with our fingers. Thus we decrease its area of cross section. That's why the flow of the liquid increases. That satisfies the ideal flow of any liquid. So the correct option is continuity equation. Okay, the aircraft of mass 4 × 10⁵ kg with total wing area 500 meters square in a level flight at a speed of 720 kilometers per hour. The density of the air in its height is 1.2 kilogram 2 kg meter per meter cube, and the fractional increase in the speed of the air on the upper surface of its wing relative to its lower surface is, we have to find the increase in the air on the upper surface, we have relative to its of the wing relation to its lower surface. Okay, so firstly we'll find the pressure difference which will be there on the upper and the lower surfaces of the air, and then we'll go with the Bernoulli's theorem, which will give you the velocity, which will give you the change in the velocity fraction, change in the speed of the air on the upper and the lower surfaces. Okay, so we have the option 0.04, 0.08 or 0.17 or 0.38. So basically first we'll find the pressure difference. So here the weight of the aircraft, it is balanced by the upward force due to the pressure. That is, the total weight of the aircraft is balanced. It is balanced by the total pressure by the upward force due to the pressure. It is balanced by the upward force, and that is due to the pressure. So that becomes the pressure on the surface area. So that is, there are two pressures. The pressure will be on the upward and the downward. So that weight, it is equals to mg, which will be the change in the pressure on the upward and the downward pressure difference multiplied by the area. So that delta P becomes equals to mg upon A, where m is given as the mass. So the total wing mass of the aircraft is 4 × 10⁵ multiplied by g. We have given the g to be 10 upon the area, which is 500. We have 500 meters square area. So the change in the pressure comes out to be 4/5 into 10⁴ Newton meters square. Okay, Newton per meter square. This is the change in the pressure. Now we'll be dealing with the Bernoulli's equation. Okay, so in here what the Bernoulli's theorem states, that using Bernoulli's theorem we have pressure plus half rho velocity square will be equals to P2 plus half rho V2 square. Okay, so we'll do some substitutions, we'll do some cancellations and transferring things out here. So P1 minus P2 will be equals to half rho, this will be V2 square minus V1 square. Okay, so P1 minus P2 will be the change in the pressure, that is delta P, which is rho upon 2 a square minus b square, that gives you a plus b into a minus b. Okay, where this a plus b upon 2, that is v2 plus v1 upon 2, this thing will be the average velocity, so we can take it as v. So we have rho velocity average into v2 minus v1 delta p. So we can change the equation to v2 minus v1 is equals to delta p upon rho velocity average. Okay, so that will give you the theorem. Okay, so we got the equation v2 minus v1 delta p upon rho v velocity average. So velocity average will be equals to v2 plus v1 upon 2, that is over here. So we'll find the average velocity. That comes out to, the average velocity is 720 kilometers per hour. So we convert it into seconds, so that is 720. We know the conversion factor 5 upon 18, so that gives you 200 meters per second. Okay, that is the average velocity. So in order to average out, we'll divide averaging by on both the sides. So average velocity on both the sides, delta p upon rho, this becomes average velocity square. So we have delta p, that is 4 upon 5 into 10 raised to 4 upon the rho value is 5 into the density is 5, the density into the average velocity, that is the density given is 1.2 into average velocity is 200 square. So calculating out, it comes out to be 0.17. So this much of the air, of the speed of the air will increase from the lower from the upper. This much is the increase of the air on the upper surface to its wings with relative to its lower surface. Okay, so the correct answer is 0.17. Okay, iceberg floats in seawater with a part of it submerged. The percentage fraction of the iceberg submerged is, we have given the density of ice 0.9 gram centimeter cube per centimeter cube, density of the seawater 1.1 gram per centimeter cube, and the options are 18%, 12%, 10% and 8%. We have to find out the percentage of fraction, the percentage fraction of the iceberg submerged inside the iceberg submerged inside the seawater. So we'll take V, that is the volume, V with the volume of iceberg, and let X be the iceberg which is submerged. Okay, sorry, let X be the, we can take it, let X be the volume which is out of the seawater, okay. So iceberg, so the iceberg floating on the seawater will be the volume into the density of ice, which will be equals to the total volume minus the volume outside the seawater into the density of seawater, okay, multiplied by gravitational constant. So we get this formula. So we have V of the icebergs into the density of the ice, which is given to be 0.9 into G, which is V minus X. Over here also the density of the seawater is 1.1 into G. We get is 0.9 V is equals to 1.1 V minus 1.1 X. So taking V on that side, we get 0.2 V, which is equals to 1.1 X. Okay, so we have the ratio X upon V, which is equals to 0.2 upon 1.1. So we need to find the percentage fraction. So for that percentage fraction, what will be, they will be taking the percentage of this ratio, that is X upon V into 100. So that is X, we have 0.2 upon 1.1 into 100, which comes out to be 18%. So your correct option is 18% of the fraction of the iceberg is submerged. Okay. The flow of blood in a large artery of an anesthetized block is diverted into the venturi meter. The wider part of the meter has a cross-section area equal to that of the artery, that is 10 mm square, and the narrower part has an area 5 mm square. The pressure drop in the artery is 22 Pascal. It is 22 Pascal. The density of the blood is 1.06 into 10 raised to 3 kilogram per meter cube. The speed of the blood in the artery is, we have to find the speed of the blood in the artery. The options given are A 0.1 to 0.12 meter per second, 0.62 meter per second, 0.24 meter per second, and 0.42 meter per second. Okay, so basically here we have given the cross section area of the wider part, so we'll take it as capital A, cross section area, that is 10 mm square, and then the cross section area of the narrower part we'll take it at small a, that is 5 mm square. Then we have given here is the density rho of the blood, which is 1.06 into 10 raised to 3 kg meter per meter cube, which can also be taken at 1060 kg per meter cube. Okay, that will be the density. Now the speed of the fluid through the wide neck is given with this formula, which is equals to V under root 2 P1 minus P2 upon rho into this A upon A minus 1 the whole square raised to minus half. Okay, this is also inside that, so we'll apply this formula. So we have A upon A the whole square, which is equals to the A upon A will be 10 upon 5, that is gives you 2 square, that gives you 4. So we have to put that 4 out here, minus 1, that becomes 3. Okay, so we apply the formula again. So we have now is V, which is equals to under root 2 P1 minus P2 upon, I'll write the formula, into A upon A the whole square minus 1 raised to minus half. So we have 2, and the pressure difference between them is P1 minus P2, we get this to be 22 pascals. Okay, it is given, and the rho, that is 1060 into this A minus A square gives you 2 square, that is 4 minus 1, then which is giving you the value 0.12 meter per second. Okay, so that much is the velocity of the blood in the wider part. Okay, an ice block having two similar metallic pieces is floating in a water in a vessel as shown in the figure. After some time the ice melts completely, then the water level rises in the liquid, the water level falls in the liquid, the water level does not change, the water level may change or fall depending upon the ratio of the mass of the ice and the melting pieces. Okay, so basically what we have is we have a vessel out here in which there is water. Okay, and then we have a ice block, okay, in which we have two masses, two similar metallic pieces of the same masses, and this ice block is going to melt. So after some time, basically when we keep the metal block, the ice block inside with the metals, due to the weight of this metal, of the metal boxes and the ice blocks together, it will raise the water level in the vessel itself. So after the ice starts melting, the water level will start slowly decreasing. So the water level in the vessel falls in the vessel. Okay, so the correct option is B. An adulterated sample of a milk has a density of 1032 kg per meter cube, while the pure milk has a density of 1080 kg per meter cube. Then the volume of the pure milk in the sample of 10 liters of adulterated milk is A 1 liters, B 2 liters, 3 liters, D 4 liters. Okay, so what we have given is the mass is the adulterated milk and the pure milk. So the mass of the adulterated milk will be its density into its volume. Okay, so the density of the adulterated milk is given here is 1032 into the volume of the adulterated milk is 10, as 1 liter is equals to 10 raised to minus 3 meter cube. Okay, so 10 liters will be 10 into 10 raised to minus 3 meter cube of much of volume, so that much of kilograms. So we have the total mass of the adulterated milk, which is equals to 10.32 kilograms. Okay, similarly for the pure milk, we have rho into V. We have the density of the pure milk given to be 1080 multiplied. The volume of the pure milk is not given, so we have the mass of the pure milk, which is 1080 into the volume of the pure milk. Okay, so the amount of, that is the total mass of water added. Okay, that will be equals to the mass of adulterated milk minus the mass of pure milk. Okay, so mass of the water added, amount of water added will be the density of water into the volume of water. Again, that will be mass of adulterated minus mass of pure milk. So density of the water we have here, it is 10 raised to 3 into the volume of the water added will be the volume of the water added will be equals to the volume of adulterated milk minus the volume of pure milk. That much of water is added into the mass of adulterated minus mass of pure milk. Okay, so 10 raised to 3 into 10 into 10 raised to minus 3, that is the volume of adulterated milk, minus of pure milk, and is equals to mass of adulterated milk is 1032 into 10 into 10 raised to we have got the answer earlier, that is 10.32 minus MP, mass of pure milk is 1080 into Vp. Okay, on solving all this we get 80 of the volume of pure milk is equals to 0.32. So pure milk is equals to 0.32 upon 80. So that gives you 1.250 meter cube. So that is conversion. After converting this by 250, we get it is how much liter? That is 4 liters. Okay, so the answer is D, that is 4 liters. So that is it. We have just found the ratio, that is comes out to be 1 upon 250 meter cube, and after converting that meter cube into liters, that is dividing by 1000, we get it to be 4 liters. A body is just floating on the surface of the liquid. The density of the body is same as that of the liquid. The body is slightly pushed down, then it will come back slowly to its earlier position, remain submerged when it is left, sink in the liquid, or come out vigorously. So basically, when a body is just floating on the when a body with the density same as that of the liquid is floating on the liquid, and when it is applied and when we pushed it down, the downward force then the downward force on the body, it will increase. It will increase due to the atmospheric pressure. Okay, and because of the atmospheric pressure on the body will increase, and also due to the water column above the body, it will increase. So therefore the body, as a result of which the body will sink down, it will not come up. So the correct option is C, it will sink in the liquid. When a capillary tube is dipped in a liquid, the liquid rises to a height h in the tube. The free liquid surface inside the tube is hemispherical in shape. The tube is now pushed down so that the height of the tube outside the liquid is less than h. Then the liquid will come out of the tube like a small fountain. The liquid will ooze out of the tube slowly. The free liquid surface inside the tube is hemispherical. The liquid will fill the tube with but not come out of its upper end. So basically what happens here is we have a capillary tube, and we have dipped in the liquid. The liquid rises in the capillary tube to a height h, and then we are again pushing the tube inside the liquid, inside the water, so that the height h of the tube outside the liquid is less than the inside height h. So basically the angle of contact at the free liquid surface inside the capillary tube, it will change. Whenever we push it down, it will change, and it will change in such a fashion that the vertical component of the surface tension forces to balance the weight of the liquid column. That's why the liquid inside it will fill, but it will not come out to its upper end. So the option is the liquid will fill the tube, but it will not come out to its upper end. So the angle of contact of a liquid with a solid depends on solid only, liquids only, both on solids and liquids, orientation of the solid surface and the liquid. Basically the angle of contact of a liquid with the solid, it will depend on both the solids and the liquids itself. So the correct option is C. The work done in blowing a soap bubble of surface tension 0.06 Newton per meter from 2 cm radius to 5 cm radius is 3.1 millijoule, 1.5 and 2.51 into 4.55. Okay, so basically we have a soap bubble, and with it has got the soap bubble is blowing from the radius 2 cm to radius 5 cm. So we have two radius r1, that is 2 cm, which gives you 2 into 10 raised to minus 2 meters, and another one r2, it is 5 cm, which gives you 5 into 10 raised to minus 2 meters. Okay, so we have r1, r2. We have given the surface tension, that is 0.06 Newton per meter. Okay, so we will be finding out the work done. So for the work done, we need the formula for the work done is surface tension into the surface area increases. So for that we need to find out how much surface area is increased. We have given only the radiuses. So we will find out the initial surface area and we'll find out the final surface area. So for the initial surface area or for the final surface area, we know that the soap bubble has got two surface areas, two sides. So for the initial surface area, we have the formula. We will take 2 because it has two sides. We have the formula 4 pi r1 square because it was the initial radius r1. So that will be 2 into 4 pi. R1 is 2 into 10 raised to minus 2 square, and that gives you 32 pi into 10 raised to minus 4 meters square. So that is the initial. Now we will find out the final surface area. again the same formula, 2 into 4 pi, instead of r1 this time we'll take r2 square, so 2 into 4 pi r2 ka value is 5 into 10 raised to minus 2 square, so that gives you that is around 200, just a second, 200 pi into 10 raised to minus 4 meters square. Okay, this is the final surface area and the initial surface area. So the increase in the surface area will be the final minus initial. So increase in surface area will be final minus initial, that will be 200 pi into 10 raised to minus 4, okay, sorry, minus 32 pi into 10 raised to minus 4. So that gives you 168 pi into 10 raised to minus 4 meters square. That is much is the increase in the surface area. Okay, after finding the increase in the surface area, what we'll do is we'll find the work done. Okay, so work done is nothing but surface tension into the increase in surface area. Okay, surface tension we already have 0.06 into surface increase in the surface area, we got it to be 168 pi into 10 raised to minus 4 meters square. So after calculating 3.12 into 10 raised to minus 3 joules, we get this answer. So 3.12 into 10 raised to minus 3 joules, converting into millijoules, we'll get 3.12 millijoules. Okay, so this much of work is done. Which of the following statement is incorrect? We have to find the incorrect statement. Blood is more viscous than water. Yes, it is true. So this statement is correct. The blood pressure in human is greater than the feet is greater at the feet than at the brain. Basically, the blood pressure, the height of the blood column in the human body is more at the feet than at the brains. So basically, the blood pressure in human is greater at the feet than at the brains. This statement is also correct. The angle of contact of a mercury with the glass is obtuse. Yes, while that of the water with the glass is acute. This statement is also correct. The angle of contact with the water with the glass is forms an acute angle, whereas with the mercury it forms an obtuse angle. Spinning cricket balls in the air follows a parabolic path. No, this is the incorrect statement. So we have D. When the temperature increases, the viscosity of gases decreases with the liquid increase. While liquid increases, the gases increases and liquid decreases. The gases and liquid increases and gases and liquid decreases. Okay, so basically the viscosity of the liquid decreases with the increase in the temperature for a liquid. Okay, for a liquid, viscosity it decreases with increase in temperature, but for a gas, as the viscosity increases with the increase in the temperature. For a gas, the viscosity increases with increase in temperature. Okay, so here the temperature is increasing, so basically the viscosity for a gas should increase and that for a liquid should decrease. So for the gas increases and the liquid decreases, we have option number B. Okay, we have 8 drops of water, each of radius 2 mm, are falling through air at a terminal velocity of 8 cm per second. If they coalesce to form a single drop, then the terminal velocity of the combined drop will be 32 cm per second, 30 cm per second, 28 cm per second, or 24 cm per second. So the solution basically is that the volume of the bigger drop which will be forming will be equal to 8 times, because we have 8 drops, 8 times the volume of the smaller drop. We are using R capital for the bigger drop, small r for the smaller drop. So by cancelling out, we get R is equals to 2 times of the small r. Okay, now we come to the velocity. For the terminal velocity, we have V is directly proportional to the radius square. Okay, so we will have the terminal velocity for the bigger drop V prime, for the smaller drop we have V. So again, the terminal velocity will be the radius square for the bigger drop, and for the smaller drop will be R square. So but we have R is equals to 2R upon R. Okay, the entire square, so that gives you 4. Okay, so that is the terminal velocity of both the drops. So we have V is equals to 4 of the 4 small v, that is the velocity of the bigger drop will be 4 times the velocity of the smaller drop. that is 4 into the velocity of the smaller top is 8 centimeter per second. So that is given by 8 4 the 32. So the answer is 32 centimeters per second. So that is 32 centimeters per second. Okay. Water is conveyed through a uniform tube of 8 centimeter in a diameter and 3140 meters in length at the rate 2 into 10 raised to minus 3 meter cube per second. The pressure required to maintain the flow is given by. So we have the option 6.25 into 10 raised to 3 Newton per meter square, 0.625 into 10 raised to 0.625 Newton per meter square, 0.0625 Newton per meter square, or 0.00625 Newton per meter square. Okay, so basically here we'll use the Poisson's formula. The Poisson's formula gives you the rate of flow of velocity, which is given to be pi p r raised to 4 8 eta l. Okay, whereas each of the symbol has the different meaning. So if we change this, we can find the pressure. That then the formula goes out to be V 8 eta l upon pi r raised to 4. Okay, where here V will be the velocity, which is given out to be 2 into 10 raised to minus 3 meter cube per second. Okay, then we have eta, viscosity, that is 10 raised to minus 3. Then we have length, which is 3140 meters, that is equals to, okay, it is in meters, so no problem for that. Then we have the diameter of the tube d, which is 8 centimeters. We can find the radius to be 4 centimeters, and we can convert it into meters, that is 4 into 10 raised to minus 2 meters. Okay, put all the facts in the formula. We get P, which is equals to, V is 2 into 10 raised to minus 3 into 8, eta is 10 raised to minus 3 into length is 3140 upon pi 3.14 into radius is given to be 4 into 10 raised to minus 2 raised to 4. Okay, after solving the entire values, the pressure which you will get is 6.25 into 10 raised to 3 Newton per meter square. Okay, so the correct option is 6.25 into 10 raised to 3. Okay, now a square plate of 0.1 meter side moves parallel to the second plate with a velocity of 0.01 meter per second. Both the plates being immersed in water. If the viscous force is 0.002 Newton and the coefficient of viscosity is 0.001, distance between the plates is 0.1, 0.015 meters, 0.005 meters and 0.0005. Okay, so for the solution we have given is the side, which is equals to 0.1 meter, so the area will be 0.1 meter square. Okay, then we have the velocity, which is equals to 0.01 meter square. Okay, then the velocity is 0.1 meter per second. Then we have the viscous force, which is 0.002 Newton. Then we have the coefficient of viscosity, which is eta, that is 0.001. Okay, so here we have the force. Here we have the equation for the force, which is eta a d of velocity, change in the velocity with respect to the position. So with respect to the we can say distance. Okay, so dx ka we can get the formula eta a, then we can have is dv upon f. Okay, so eta we already have 0.01, substitute the values, 0.01 square into the velocity is 0.1 upon the force applied is 0.002. The answer for this equation comes up to 0.0005. So that much of meter of displacement is required. Okay, the flow rate of water from a tap of diameter 1.25 centimeters is 3 liter per minute. The coefficient of viscosity of the water is 10 raised to minus 3 pascals. The nature of the flow is unsteady, turbulent, laminar, or none of this. Okay, so solution we have here, we need to find whether the water flowing from this tap is a turbulent or is a laminar or is unsteady or is it none of them. So we have the diameter, which is equals to 1.25 centimeters. Converting it, we get 1.25 into 10 raised to minus 2 meters. Okay, then the density given to be rho, that is 10 raised to minus 3 pascal. Okay, 10 raised to minus 3, sorry, the density we know it is 10 raised to 3 kilogram per meter cube. I thought it was then viscosity. Okay, then comes the viscosity, it is 10 raised to minus 3 pascals. Then we have the volume of the liquid flow is 3 liter per minute. So we will find the Q, that is the amount of volume of the liquid flowing through the tube per second. Okay, we have 3 liters per minute. So we will have 3 into 10 raised to minus 3 meter cube per minute. Then we are converting it to seconds, so we will divide it by 16. So we have 5 into 10 raised to minus 5 meter cube volume of liquid is flowing per second. Okay, now we in order to determine whether it is a turbulent, unsteady or laminar or none of this, we will use to compare whatever value we are getting with the Reynolds number. So in order to find the Reynolds number, we have given the equation. Reynolds number is Re, which is 4P capital Q upon pi d eta. Okay, so here 4 is just a number, P will be the pressure, sorry, this is rho will be the density, that is 10 raised to 3, into Q will be 5 into 10 raised to minus 5 upon pi is 3.14, into the D will be the diameter, that is 1.25 into 10 raised to minus 2, into eta is 10 raised to minus 3. Okay, substituting all the values, what we get is 5095. Okay, and this number is greater than 200 than 2000. So whenever, what Reynolds has said, whenever that number goes above 2000, then the water flowing, then the streamline becomes a turbulent. Okay, so basically the water flow through this tap is a turbulent. For a surface molecule, the net force on it is non-zero. No. The net force on it is 0. No. There is a net downward force and there is a net upward force. So basically for a surface molecule, we have a net force which is acting downward. So there is a net downward force on a surface molecule. Mercury has an angle of contact equal to 140 degree with the solid angle glass. A narrow tube of radius 1 mm made of this glass is dipped in a trough containing mercury. The surface tension of the mercury at the temperature of the experiment is 0.465. The distance by which the mercury dips down in the tube related to the mercury surface outside is. So we need to find the height of the mercury which is dipping down inside the tube. So basically we have here is theta, which is given angle of contact, that is 140 degree. Then we have given r, which is the radius, that is 1 mm. We can convert it as 1 into 10 raised to minus 3 meters. Then we have the surface tension of the mercury 0.465 Newton per meter. Then we have the density of, we are given the density of mercury 13.6 into 10 raised to 3 kilogram per meter cube. Okay, next we have the formula for the height, which is 2s cos theta upon r rho g, which is equals to 2 into s is 0.465 into cos of 140, that means cos of minus 40 degree, minus of cos 40 degree. Okay, so that will bring you r radius, which is given to be 1 into 10 raised to minus 3, density is 13.6 into 10 raised to 3, into the g, gravitational constant, we can take it as 9.8. Okay, now calculating all the above values, we get minus 5.34 into 10 raised to minus 3 meter, which is 5.34 minus mm. Okay, the minus sign indicates that the mercury level is depressed inside, so we have the option A, 5.34 mm. The pressure on a swimmer 20 meters below the surface of the water at the sea level is, take the atmospheric pressure to be 1 into 10 raised to 5 pascals. Okay, options are 1 atmospheric pressure, 2 atmospheric pressure, 2.5 or 3.0. So basically we have given the height and below the water, that is 20 meters. Okay, next we have the density, we can take it as 10 raised to 3 kilogram per meter cube. Next we have the atmospheric pressure, which is 1 into 10 raised to 5 pascal. So for the swimmer, the total pressure on the swimmer will be the atmospheric pressure plus rho gh, that will be the density into the height into the gravitational constant which will be acting on it. So Pa, which is 1 into 10 raised to 5 into rho, the density 10 raised to 3 into, this is plus, into g, which we are taking it to be 9 we'll take it round up to 10, okay, multiplied by the height, which is 20. So on calculating we get 1 into 10 raised to 5 plus this comes out to be 2 into 10 raised to 5, okay. So that means that is 3 into 10 raised to 5 P of Pascal of pressure is applied, that is 3 atomic pressure, atmospheric pressure, okay, 3 atmospheric pressure. The option number D is the correct option. Surface tension of a soap solution is 0.03 Newton meter. The work done on blowing the form of the work done in blowing to the form of a soap bubble of surface area 40 centimeter square is. So we have the options: 2.4 into 10 raised to minus 4 joules, 1.2 into 10 raised to minus 2 joules, 3.6 into 10 raised to minus 4 joules, or 4.2 into 10 raised to minus 2 joules. So basically we need to find the surface area. So surface tension given is 0.03 Newton per meter. Next we have the surface area, which is 40 centimeter square. So we will be changing it to meters. So 40 into 10 raised to minus 4 meters square, okay. So that gives next we will find the work done. So work done is equals to surface tension into the change in the surface area. So surface tension is 0.03 into surface area. Change in the surface area is because it's a soap bubble, we have the it has got two surface areas, so it has got two sides. So we will be multiplying the surface area twice by 40 into 10 raised to minus 4. So that gives you 2.4 into 10 raised to minus 4 joules. So the correct option is A, 2.4 into 10 raised to minus 4 joules. Which of the following graph shows the variation of the surface tension with temperature over small ranges for water? So we have the graphs of surface tension with the temperature. So the variation will be a direct variation, that will be change in the surface area. Surface tension with respect to the temperature will be a slanting graph. So B is the correct option. It will not rise in this way, it will be decreasing in the pattern, which is it will be a steady decreasing pattern. So B is the correct option. Mercury does not wet the glass. This property of liquid is known as adhesion, surface tension, viscosity, compressibility. The property is known as adhesion. A liquid does not wet the solid surface if the angle of contact is 0, equal to 45 degree, equal to 90 degree, greater than 90 degree. Basically liquids do not wet the solid surfaces if the angle is an obtuse angle, that is it should be greater than 90. So as in case of mercury, so it should be greater than 90 degree. So an angle fluid flows through a pipe of circular cross section made of two sections with diameter 2.5 centimeters and 3.5 centimeters. The ratio of velocities of two pipes is 9:4, 3:2, root 3 is to root 2, or 2 is to root 3. So basically what we have here is the two cross sections, and we have the flow of the liquid. From the continuity equation we have A1 V1 is equals to A2 V2, okay. So we will take the ratios, V1 upon V2 is equals to A2 upon A1, okay, where A is the cross section area of them, which will be pi r square upon pi r square, r2 and r1, where the radius will be the diameters, half of the diameters. So pi d2 square by 2 upon pi d1 square by 2. So we have is d1 square by 4, sorry, we are squaring it, so it becomes 4. So d2 upon d1, which is the square, will be given was 3.75 upon 2.5, the whole square. The value comes out to be 9:4. So v1 upon v2 is equals to velocity ratio is 9:4. So A is the correct option.